This is a review video for section 8.5. 8.5 was the first section that we covered right after the quiz, and it's integrating by an algebra technique called partial fractions. What you're going to look for a problem of 8.5 is you're going to look at an integral that has to be written as a fraction. It has to have a denominator that is either factorable or already factored, and I'm going to show you an example of each today in this video. So if you look at this one, this is what I would call kind of like a basic level type problem with this. This is what we would have talked about kind of the first day that we worked with partial fractions. First thing you want to do is you want to factor the denominator if it's not already factored, and this factor is x plus 7, x minus 3. And then we're going to break it up into our partial fractions. They are both linear factors, so I can write it as a over x plus 7 and b over x minus 3. The next one I'm going to do will have a factor that's not linear, and we'll talk about the adjustment that's necessary with that. So my first step, once I have it written as this partial fraction, it's called a partial fraction decomposition, is to clear fractions. So I'm going to multiply everything by the common denominator, x plus 7, x minus 3. And when I do that, this entire denominator will cancel, so I'll be left with 7x minus 1. When I do that with the a term, the x plus 7s will cancel, so I'll be left with a and an x minus 3. And then when I go to the last term, the x minus 3s will cancel, and I'll be left with a b and an x plus 7. At this point, there's a couple different options the way to solve. When you're working with factors that are linear, the fastest way to solve this is to do what's called a substitution or a choosing x's method. Pick x's that will allow things to eliminate. So, for example, if I let x equal 3, plug it in. Don't forget to plug it here. That's a common mistake, is forgetting that. When I plug 3 in, I get 21 minus 1, so I get 20. When I plug it into the a term, it will cancel, so I don't have to worry about that. When I plug it into the b term, I'm going to get 10b. So with a quick division, I now know that b is 2. Now I'm going to do the same thing, but this time I'm going to choose x to be negative 7, because that's going to eliminate one of my terms. When I put negative 7 in the left side, I'm going to get negative 49 minus 1, which is negative 50. When I put it into the a term, I'm going to get negative 10a. And when I put it into the b term, it will cancel. So I divide both sides by negative 10, and I get a to be 5. So essentially what you've done is you've figured out a new way to write your integral, and it's going to be written as a, which is 5, over x plus 7, and b, which is 2, over x minus 3. This is equivalent to the original integral, but the original integral wasn't possible to integrate, so now it allows us to break it down. That's why it's called a decomposition, kind of break it into separate parts that are easy to work with. Both of these are natural logs. Both of them are du over u. Both of them have the coefficient come out front, so you can write your answer as 5 natural log of x plus 7 plus 2 natural log of x minus 3. That's one possibility for writing your answer. Another possibility is that you make both of these coefficients powers, so you can write it as the natural log of x plus 7 to the 5th plus the natural log of x minus 3 squared. Or you can actually go one step further, and you'll see this a lot of times on multiple choice, is they use one more logarithm rule, which says when logarithms are added, they can be multiplied. I'm not sure why my marker's going crazy. Sorry about that. So I get the natural log of x plus 7 to the 5th times x minus 3 squared plus c. And you'll see that happen a lot with logarithms, because you end up with so many logarithms, is they'll use properties like the power property, like the product property. So you want to look for that when you're doing a multiple choice to see if they use logarithm properties to rewrite it. The other thing you want to look for on a multiple choice question is make sure they actually want you to do the full problem. You will have problems that only want you to get to this step right here. Essentially, they're making sure that you can find the a, the b, or however many unknowns there are and set it up, but they're not asking you to actually go through the integration a lot of times, because the integration is very easy anyway, so they're more concerned with can you actually go through the algebra process and set it up. The second one, again, my pen is having a mind of its own lately, so I'm sorry about that. Let me get rid of all this. This one I would call kind of a level 2 difficulty. This is definitely a much more challenging problem. for a couple reasons. The main reason, what you might notice right away, is it has a factor that is not linear, the x squared plus 1. In addition, it's going to take a little more work to find your unknowns. So when we start this problem, nice thing is it's already factored, so we don't have to do that. But we do have to break down the composition a little bit differently. Since the first factor is quadratic, I need to write ax plus b as the numerator when I break it up. Since the second factor is linear, I can just write it as a c over x minus 3. I'm going to clear fractions, so I'm going to multiply everything by this denominator. When I do that, I'm left with just a 5 on this side. I'm left with ax plus b times x minus 3. And I'm left with c times x squared plus 1. There's a couple ways to do this. Now, you could go through and choose x's and do more of a substitution method. The only disadvantage to that here is there's not a lot of ideal x's. For example, I would let x be 3 because that would cancel a lot of things. But then at that point, you would have trouble finding other good x's. You could use 0, you could use 1 or -1 because they are small numbers, but none of those are very efficient. So I'm going to show you the other technique that we did the second day in class, which was, I called it kind of equating coefficients or matching coefficients. To do this, we have to multiply this out. So I'm going to FOIL this together. So I get ax squared minus 3ax plus bx minus 3b plus cx squared plus c. And now what you want to do is you want to go through and see how many terms do we have of each degree. So how many x squareds, how many x's, how many constants. So on the left side, I have 0 x squareds. On the right side, I have a plus cx squareds. On the left side, I have 0 x's. On the right side, I have -3a and b x's. On the left side, I have 5 as my constant. On the right side, I have -3b and c as my constants. So I turned it into a system, and you have a couple options here. Obviously, if you have a calculator and you're comfortable with matrices, you're welcome to write it as a matrix. I'm going to actually take you through and show you by hand. I went through and did this one earlier, and here was the fastest way I found to solve it by hand. I figured out what b and c were in terms of a, so I came off to the side and said c is equivalent to -a, just solving for c in the top line, and b is equivalent to 3a, just solving the second line for b. And then I took both of those pieces of information and I plugged it in this third line. So I wrote it as 5 equals -3 times 3a plus a -a or minus a. So I get 5 equals -9a minus a. So 5 equals -10a. So a equals -1/2. Now that I know that, I can come back up here and say, well, that means c has to equal +1/2, and b has to be equal to 3 times -1/2, so -3/2. So already you can see this problem is a little more involved because of the work it takes to find the unknowns. Now when we set up our integral, now that we know what a, b, and c are, we'll have the integral of -1/2 x minus 3/2 over x squared plus 1, that's plugging a and b back in, and then plus 1/2 over x minus 3. This one is also going to be more difficult just to integrate, so that's why this is definitely a higher level, more of a challenging type problem. The first integral, hopefully you look at this and think, I need to pretzel this, I need to split it up. So we're going to split it up into -1/2 x over x squared plus 1 and -3/2 over x squared plus 1. And I'm going to deal with this piece later because this is going to be a very easy integral. I just want to make sure when I'm all done, hopefully I remember to tack that part on my answer. The first one, the u is x squared plus 1. du is 2x. So we will have a 1/2 adjustment, plus we have a -1/2 that we have to bring out front. So we're going to have a -1/2 and then another half. So we're going to have a -1/4. And it's a du over u, so we get the natural log of x squared plus 1. This one is going to be an arctangent. U is x, du is just dx, so no adjustment. A is 1. We do have to bring the coefficient out front, so we're going to have -3/2 arctangent of x. And now I'm going to go back up and do the part that I circled. That is just a basic natural log. The 1/2 that is on top, this right here, does need to come out front. So it will be 1/2 the natural log of x minus 3 plus C. As far as different things that you could see answer-wise, you may see this 1/2 that you wrote at the very end written as a power. So you could see that last term be the natural log of the square root of x minus 3. You could also have this be written as a power. But other than that, you're really not going to see as much combining on this one. The work here is more challenging with the algebra in the beginning and the integration at the end, so you're probably not going to see a lot of changes in the final answer. They're going to pretty much leave it as is. So that gives you an idea of 8.5, basically taking you through a simple version, one that is a basic linear factors where you're solving by substituting x values in, and then one that is a higher level difficulty where it has a quadratic factor, plus I solved it a little differently. And I definitely could have solved it the way I solved the last one, but it still would have involved a system and it would have taken a little work to find the A, B, and C.